Welcome students, and in this video we are going to talk about Riemann problem. Okay, so in the last video, so this is a continuation of our study of conservation laws, and in the last video we looked at a problem, right, that if you remember, ut plus ux is equals to 0. That's the problem given to us, and u at, let's say, x0 is given to be 1 for x positive and 0 for x negative. Okay, or the other way around also we did, right? So that's not the point. The point is this: see, we want to kind of generalize this problem. Okay, and what we need to do for that is, first of all, let us write down the proper Riemann problem. So this is from the earlier class, or earlier video, whatever you want to call it. So we consider this problem. So the Riemann problem is for a general problem, right? ut plus f of u, clear, with respect to x, that is going to be 0 for t greater than equals 0 and x in R. Okay, and we also assume u at the point x0 is going to be some phi of x. Clear? Now, what is phi of x and all that, we will just write it down. So here phi of x is a very special function. Okay, so this problem is called a Riemann problem. Okay, so let me write it down. Number this is 1. Okay, 1, and phi here phi of x is a piecewise constant function. Okay, piecewise constant means it is something like this: u minus we will write it for x negative, okay, and u plus we will write it for x positive. So basically, from left, if you are looking at it, we will call it a u minus, and from right we will call it a u plus. This is some constant, u minus u plus. This is nothing to do with, if you guys know what u minus u plus, there is another notation, right, that if u is a function, u plus u, here we are not assuming something like this. So u plus u minus is a maximum, minima, that sort of thing. It's not that. U plus u minus is some number. Okay, some number. Yeah, so u minus is from left, so x is negative, u minus, x positive, we are just assuming u plus. Clear? No information on x equals to 0 is given. Okay, and so this is phi, and what is f? So f here also, f is uniformly, very important. Okay, f is uniformly convex. Clear? F is uniformly convex, and the initial data and the initial not the initial data, uniformly convex. So let me write it down what the uniformly convex means. So if is uniformly convex, that is, okay, what does it means? It means that there exists, okay, a theta greater than 0 such that, okay, very important, please understand, you guys know all about convexity, right? If f is convex, so let's say if f is a C2 function, or maybe C infinity, let's just stuck with C infinity. F is the C infinity function which is convex, Now we all know that if that is the case, f double prime has to be greater than 0, right? That is convexity. So f double prime can be greater than 0 means, f double prime for some sequence xn, it can happen that f double prime of xn can converge to 0. It can happen, right? It can be as closer to 0 as possible. But if it is uniformly convex, it means that for there exists some theta positive, okay, such that f is bounded by that theta. So f double prime is bounded by this theta such that f double prime is greater than equal theta greater than equal 0. So basically it is bounded below by that theta. So it cannot arbitrarily go towards 0. Clear? Okay, so this case cannot happen. This is uniformly convex. This is convex. If f is convex, f double prime is positive. That you guys already know. Here it is called, we are saying more, we need uniform convexity. Uniform convexity is, it is bounded by a positive number, however small it might be. Clear? Okay, now just for fun, you guys can obviously try and find out a uniformly convex. So this the example of this thing I will not give it to you. You guys have to find it yourself. Okay, so so this is for a small exercise for you guys. Exercise: find f from R to R. Of course, it will also be in the assignment, but anyways, let's just put it as an exercise here. F from R to R, which is uniformly convex. Okay, of course you do realize that whenever we are saying uniformly convex, we are assuming that f double prime exists, right? So basically, of course, assuming f is smooth, f is at least C2 or C infinity. I mean, here it is not a very, precise thing. You can take C infinity, you can take C2, but for, C2 is fine enough. You don't worry about it. Okay, so let me write it down. So this problem 1. Okay, the problem 1. So basically the equation, this equation along with this data, where the data is, this is a piecewise constant data. Okay, we call it a piecewise constant data. We have looked at two different problems, right, with piecewise constant data. So if the data is piecewise constant and f is given to be uniformly convex, in that case one is called the Riemann problem. Is it fine? It's called the Riemann problem. Okay, this is after the great German mathematician. I am absolutely certain that all of you guys have heard about Bernard Riemann, right? So this is after him, Riemann problem. Okay, so that guy has contribution in everything, it looks like, yes, from geometry to integration to everything, right? Okay, so this is that Riemann. Okay, so let's look at the problem in a more precise way. So essentially we are writing down a theorem. So this is a theorem. By the way, you see, the whole of whatever we did up till here, all the second order equations which we have studied, heat equation, wave equation, and Laplace equation, and now this conservation laws which we are studying, I am doing all of that from Evans. Okay, it's just some precise explanation. Evans book is not a very easy book to follow by yourself if you are doing it for yourself for the first time. So this is just an explanation, for my explanation, how I understand Evans, and that I'm just writing that down. Okay, so the theorems are exactly like Evans. Okay, so let me write it down. Of course, in this video, whenever we are talking about phi and whenever we are talking about f, these assumptions are assumed. Okay, these are assumed. On phi and f is assumed, right? That until we say otherwise. Okay, so given phi and f, of course f is given to be uniformly convex, if you remember. Okay, given phi and x, there exists a unique, very important one, unique, this means unique weak solution. Okay, unique weak solution. So basically you have two part of the well-posedness, unique weak admissible solution. Okay, you guys already know what is admissible solution. So basically the Rankine-Huggenite condition is satisfied along with the entropy condition, right? Solution to the Riemann problem. Okay, to the Riemann problem 1 to 1. So basically let me write it as 1. Clear? Okay, so number 1, so essentially what do we have? If u minus, so the wave on the left, okay, is greater than u plus, so the initial condition, not here wave. So basically it is the height of the wave at t equals to 0. Okay, so if that is greater than the height is more than the wave on the right, okay, then the admissible solution okay, has a shock curve. You remember that curve, x equals to psi t, okay, has a shock curve of speed sigma. Okay, of speed sigma. You remember speed, which is f prime of xi prime of t, right? And the solution is given by okay, so it is basically telling you what is the solution. U of xt is going to be u minus, this is for x less than t sigma. Clear? Okay, and u plus, which is x greater than t times sigma. Okay, Now, don't get confused here. I am just writing down what we have learned in the, we looked at two different examples, right, in the other video. So, whatever we have learned from that, we are taking intuition from there and we are writing down the theorem. We will, of course, prove this thing, yeah. So, basically, what it is saying is for x less than t sigma. So in our earlier case, if you remember, sigma for f is u square by 2, sigma was half, right? So at that case, u is u minus for x less than t by 2 and u plus for x greater than t by 2. You can just compare it with your other example, okay? And number 2, if u minus the wave on the left is the speed is less than that, u plus on the right, then the solution, then you remember what happened? There was a gap, right? That rarefaction gap. Then the solution has a rarefaction wave. I hope you remember this one. Yes, this was the gap was there in that xt plane where we could not find a solution, right? Okay, so that is the rarefaction wave, and the solution is given by, if you remember how we did the solution, so we can write it with the shock wave also, but that was giving us the wrong entropy condition, okay? So the right entropy condition is given by, so the solution which satisfies the right entropy condition is given by, if you remember, that was given by some x by t, right? So here we will write it in a more general way. xt will be given as u minus, clear, for x less than f of u minus, f prime of u minus times t, okay? G, capital G, I will write it down what capital G is. So in our earlier case, the earlier example which we just did, okay, just did means in the other video, the second example, in that case g of xt was actually x by t, okay? So that was because of our initial condition, okay? So don't worry about, that is just for our initial condition. This is just a general version of that, okay? So u minus less than x by t less than f prime u plus, okay? I hope this is fine. And u plus when x by t is greater than f prime of u plus, clear? So what is g here? Here where capital G is f prime, the inverse of that, okay? The inverse of that, the inverse of f prime, okay? Fine. Now one question, this is I want you to ask, I will not be answering it right now, okay? What I want you to do is this. So this is a question for you guys, think about it. Why do you think that the inverse of f prime, not f inverse, f prime exists, okay? We certainly did not start with f is bijective and everything, right? F prime is bijective and all. We did not start. So why does the inverse exist? That is one question which I am leaving it for you guys to think about. Okay, so let's prove this theorem and then we'll go from there. Okay, so proof. So first thing first, to proof. Now, of course, you see the first problem. See this problem number 1. See u is given by u minus for x by t less than t and u plus for x by t greater than t. Okay, so do you think it is a classical? You see. In either side of the curve, there is a curve x equals to sigma t. On either side of the curve, this is going to be what sort of thing? This is going to be a classical solution, right? On either side of the curve. Okay, if you remember, so you see, because this is a constant function, right? It's a constant function. It satisfies the, it satisfies the equation. There is nothing to prove there, right? You can just put it there, and it's constant. So there is nothing, whenever you do ut and you calculate ut, and if you calculate ux, it's going to be 0. So you don't worry about all that. It is definitely going to satisfy the equation. That's not a problem. And anyways, they are classical. I mean, they are smooth in either side of the curve x equals to sigma t, right? And that will actually guarantee that you have a it's a weak solution. Yeah, why it will guarantee? Because I mean, it will satisfy the Rankine-Hughenot jump condition also. Okay, because it is given like this. You see, it is given like this. I mean, yeah, because this sigma is I mean f prime of t. The whole how do I put it? You see, the whole solution is constructed thinking of all of that condition in mind. So definitely this is going to see sigma is what? Sigma is f prime of sorry, not f prime, sigma prime. Sorry, xi prime, xi prime of t. If you remember, okay, that's the speed, right? Okay, so you see what is happening here is this. I mean, the whole if you think about it. This whole solution is set up in such a way that it has to satisfy the Rankine-Hughenot condition. This is the Rankine-Hughenot condition, right? I mean, if you want, you can just write it down: f of u plus f of u minus by u plus by u minus. That is f prime of t. Okay, so all of that is already satisfied. So this is going to be a weak solution. There is nothing to prove here. Okay, and of course, yeah. So and why it satisfies the entropy condition? Because u minus is greater than u plus. It is given here. The entropy condition is given here. Okay, so it will satisfy the entropy condition. So I mean, what I am trying to say is this: I am going to skip the first problem. It is not a very difficult thing to see, and I am quite sure you guys can understand that. Okay, this condition, why we need it? This is just to guarantee the entropy condition, and this I mean, after that, whatever the solution is, that is that is actually constructed keeping the curve of discontinuity in mind, so that the Rankine-Hughenot condition is satisfied. I hope this is fine. Okay, now let's look at the second problem. That is important. Okay, second problem is important, and let me prove that part. Okay, so the second, let me write it down. It will be better. U of xt. So I want to show this is our weak solution. Okay, this is our weak solution. U minus for x by t less than f prime u minus g, capital G of x by t. Okay, this is for f prime of u minus less than x by t less than f prime of u plus. Okay, and u plus for x by t greater than f prime of u plus. Okay, g is, of course, if you remember, we wrote it as f prime, the inverse of that. Okay, where right now, so now what we are going to do is basically we need to check that you see, first thing first, let's say, I mean, if you draw this x by t kind of thing. Okay, let's say I'm drawing x t, and let's say this is our curve. Okay, x equals to sigma t. Okay, and I mean, we did this sort of thing. So basically, sorry, let me draw it like this. Okay, let me draw it like this. See, for x less than, so let's say this is the path. Okay, this is the place where it is u is g by x by t. Okay, so u equals to g of x by t in this place. So u is u plus here, and u equals to u minus here. Okay, I'm just drawing something randomly. Yeah? This is nothing, I mean, it's not like a precise thing, something in this. Let's say that is your x by t equals to f of f prime of u minus. Okay, and this is f prime of u plus. X by t equals to f prime of u plus. Okay, so I mean, of course, I'm just arbitrarily just drawing some stuff, and here you see in this part of the domain, u equals to u minus. So that's a classical solution in this part. Again, u equals to u plus in this part of the domain. Okay, so that's a classical solution. So we are only interested in finding out if this is valid or not. Okay, so basically we are looking at the left of this particular thing, and on the right of this thing. So this region R, let's call it R. Okay, so we need to check. I hope this is fine. U is a solution in this place, a prime u minus less than x by t less than a prime u plus, because the other two parts they are classical. Okay, now let's just do that. So how do you check it? It is if it is classical solution, this has to satisfy ut plus f of ux, right? So what is it? It is, the first thing first, we have to use chain rule here. So ut, u is g by x by t, so it is g prime of x by t and then the derivative of t, so which is minus x by t square. Chain rule, clear? Plus the derivative of this thing, this is f prime of ux. Okay, so ux is g of x by t, clear? G of x by t times ux, right? F prime of u, f prime of u times ux. Okay, see, f of u, the derivative of that is f prime of u times ux, right? Okay, so I'm just writing it down. So f prime of u is g by x by 2 and then ux is g prime of x by t and the derivative of x by t, which is 1 by t. Okay, derivative of x, I mean x by t with respect to derivative with respect to x, that is 1 by t. I hope this is clear. Okay, so now you see what is happening here. Let us write it down. It is g prime of x by t minus x by t square. Okay, and what you see, what is g? G is f prime inverse, clear? So f prime of f prime inverse x by t. Okay, so that is 1. So it is essentially, I am left out with g prime of x by t times x by t square. Okay, so x by t from here it is coming and 1 by t from here it is coming, so essentially x by t square. Yeah, I hope this is fine. Okay, so yeah, now what do we have? Okay, what do we have? So this is basically the same here, so this is 0, clear? Okay, therefore u is classical in all the three, classical in each of the three regions, right? Each of the three regions, in each of the three regions where it is defined. Okay, now so also, okay, along the curve x by t equals to f prime u minus, this curve f prime u minus. Okay, g of x by t, clear? This is f prime inverse of x by t. Okay, that is given by u minus, clear? See, x by t equals to f prime u minus, so f prime inverse of x by t is u minus on that curve. Okay, along that curve, this curve. Okay, now along this curve, now we just I mean you can do the exact same thing. Yeah, you can do the exact same thing. Along this curve you can show that g by xt is u plus, clear? Okay, therefore u has no curve of discontinuity, so u is continuous, right? No curves of discontinuity, okay, and thus satisfy the entropy condition. Okay, and that satisfies the entropy condition. Okay, so and now yeah, so it is done. So it satisfies the entropy condition. There is no I mean and it is classical in each of the regions R. So I mean there is nothing else to do. It is going to be a weak solution. Okay, hence therefore I mean I don't have to write it. So hence u is a weak solution and we are done. Okay, so maybe I can end it here. Okay, the theorem. Yeah, I hope this is clear. Nothing to do here. Actually, you see the point of all of this is the solutions here in both the cases were constructed in such a way that how do I put it, that whatever we want the solution does, the solution, we are actually manipulating the solution. That's the point, you do understand. So that is why it is bound to satisfy. We have manipulated the solution, and here also we did the exact same thing. It's just a little complicated here because of the capital G. Otherwise there is nothing else to do. Okay, so it is a the rarefaction, the solution is a rarefaction wave in that case. Okay, of course it is the admissible solution. Okay, it's the admissible solution. So now we are done. Okay, so you see we are done here. Okay, so let's finish the proof here. Okay, and let's look at one another example, and then we are going to finish this lecture. I think this example will make things more precise. Okay, that will be better. So this is example 3, I guess, of this conservation law. So you have this problem, ut plus ux equals to 0. Okay, u at the point x0 is phi of x. Okay, this is for x in R and t positive. And what is phi? Where phi of x is given to be 1 for x between 0 and 1 and 0 otherwise. Okay, now of course we already know, so this is a Burger's equation. We have solved it many times. We already know what are the characteristics curves. So the projected characteristics, I am not proving this thing here. The projected characteristics curves are given by, so again let me explain to you. In this course we had taken something for always, as far as in my control, I have always used consistent notation. So you see, whenever we write R here, if I am parameterizing a curve C with R, that is always the parameterization of the data curve. Clear? That is always the parameterization of the data curve. So in this case, that data curve will be given by R0 phi of R. Right? R is in R. Okay, and the characteristic curves is parameterized by, so let's say the characteristic curves is given by I don't know, maybe some p, but that is always parameterized by S. Yeah, the characteristic curves are always parameterized by S. So here the projected characteristics are given by x of RT is equals to phi of RT plus R. Okay, and where is this R varying? R is varying in R. Clear? X and T is given to you, and this is the other projected characteristics. Clear? So now let's look at the cases. So case 1, if R is negative, okay, then what is phi of R? Phi of R negative, it is going to be 0, right? It is going to be 0, which implies x is equals to, phi of R is 0, x is equals to R, okay, and what is u along these curves? If you remember, you see, if you remember the characteristics thing, this z prime of Rs, okay, z prime of Rs, this prime is with respect to S, this is equals to 0, right? Okay, so u is constant along these curves, right? And since phi of R is going to be 0, okay, so u is equals to 0 along x equals to R. I hope this is clear. Z is constant. So what is Z? Z is defined by, if you remember, Z of Rs is given by u of x Rs y Rs, right? That is how we define Z. Now you see, Z is constant along S for a fixed R. Z is constant. This is one of the characteristic equation, right? Z is constant along S. At S equals to 0, phi of R, so at when S equals to 0, in the starting, phi of R is given to be 0, right? So Z is constant along the characteristic curves, and at the origin S equals to 0, it is 0. So basically Z is 0, and hence u is 0 along these curves x equals to t. I hope this is clear. Okay. Now, if 0 R lies between 0 and 1, then what happens? Then phi of R is going to be, you see, 1. Okay, phi of r is 1. Okay, and that will imply x equals to phi of r is 1, so this is t plus r. Clear? And what is u in this case? Phi of r is 1, so initially if u is phi, right? At s equals to 0, u is phi, so z is phi, basically z is u, so hence u is going to be 1 along this characteristic, along these curves, along x equals to t plus r. This is fine. Okay, u is constant. Remember, what it does at s equals to 0 goes forward along the characteristics. At s equals to 0, phi of r is going to be 1, so z is going to be 1, so u is going to be 1. Clear? Now, if r is greater than 1, okay, then what is r greater than 1? 0 otherwise. Okay, so phi of r is again going to be 0, and that will imply x equals to r, the first case, and u is equals to 0 along these curves. Okay, x equals to r. Okay, so when r, so essentially what all of this means is when r lies between 0 and 1, okay, x is t plus r. When r lies between less than 0 or greater than 1, x equals to r are the projected characteristics. Here, okay, so let us draw some curves. Maybe let me draw it here, it will be better. Okay, and yeah, so again the drawing part is there. This is so okay, so these are the some characteristics. Okay, so this is for r negative. Clear? R negative, x equals to r, that is why these are the characteristic curves, right? So this is r, this is r, and this is x. Okay, this is x. Okay, now for x greater than 1, so let's say that's your 1. Okay, x greater than 1, the curves are given by x equals to r. Clear? Okay, I hope this is fine. Okay, and x equals to t plus r in the middle, between r between 0 and 1, it's t plus r. So it will go on doing this now. I think this is the best I can draw. I'm sorry about it. I think this is more or less fine, but okay, let me, this does not okay, so I think this is fine. Yeah, okay, so anyways, you get the idea. Okay, so these are the characteristic curves. So now let's look at it's fine. Okay, so you see, in this part of the domain, there is absolutely no problem. Okay, there is no problem. Here the issue is up till this point, if you just, it does not touch 1, but as far as if it goes near 1 also, then also it will go on doing this thing. After that, this part there is no problem. This part sorry, let me, yeah, it's gone. There are so many lines are gone. One second, let me draw. Oh god, 1 second. I'm sorry about it. So I hope this is fine. Okay, see, what I'm trying to say is this: at x equals to, so okay, x equals to 1, let's say that's the line. Okay, so up till here there are problems. From 1, so x equals to 1, from 1 there are no problems. So in this part there are no problems. Okay, but here the characteristics crosses, here there is a gap. Okay, so one thing, the first problem is there is a gap in this part, and there are, the characteristics, they intersect in this part. So we have two different problems here. How do you deal with that? Okay, so So between x equals to 0 and x equals to t, we have our familiar thing, right? X equals to 0 and x equals to t, we have a gap. X equals to t, we have a gap. So there is a rarefaction wave, right? You remember we did this kind of thing earlier, right? And you see, when it touches, when these things touches here, these are the curves where they are intersecting, the characteristic curves intersect. So essentially those are the shock waves. Okay, so and a shock is formed by the intersection of the line, which line? X equals to t plus r, and which line, if you remember, x equals to 1, right? This is for r between 0 and 1. Please remember, r between 0 and 1. Okay, so you see, x equals to 1 line was the problem, and after that everything is problem. That's not the point, but x equals to 1 only, it is the first place where they are intersecting. So the first shock is from at that point. Okay, those lines, not the point, and that line. Okay, so now let's use the Rankine-Higuenot condition. Now the RH condition, again, as you remember, I am always telling you, see, there are certain things in this PDE course which I am going to always take it for granted. RH condition, whenever I am writing, it means Rankine-Higuenot condition. Okay, for example, let's say if I write out capital phi, write this, of x minus y, what do you understand from there? This is the fundamental solution of the Laplace equation. You don't have to worry about all that. It is always, if it is not mentioned, please remember, the capital phi, if it is written like this, that's the different phi. Okay, capital phi, if it is written like this, always assume it has to be a fundamental solution. Okay, so x minus y it is given, it is a fundamental solution for a Laplace equation. Let's say if it is written like x minus y times t, something like this, then that's a fundamental solution for the heat equation. Clear? So always assume the capital phi, this will be always assumed to be a fundamental solution for our in our course as either Laplace or heat equation. Clear? So but small phi, that generally we use it for different purposes. Most of the times we use it as a initial condition. So here you see, if we used it as small phi, this is just an initial condition. This is not a fundamental solution or anything, it's just an initial condition, some function phi. Whenever I am writing phi like this, okay, anywhere, even in the exam also, if I am writing phi like this, always assume that is going to be fundamental solution unless anything explicitly is mentioned. Is this clear? I hope we are not getting confused here. This is capital phi, this is small phi. Okay, right. So again, here also, whenever I am writing RH condition, always assume RH condition is a Rankine-Higuenot condition. Okay, I am not going to explain it all the time. Okay, so by RH condition, what does it mean? That the speed sigma, okay, of the shock must satisfy what is it? The jump of f of u by the jump of u, right? Okay, and that is u plus u plus pi 2, because f is here, f is given to be u square by 2. See here, f of u is u square by 2, right, in our case. So this is u minus plus u plus by, which is u plus u minus is, you see, u minus here, this is going to be here, u minus is 1, okay, and u plus is 0, right? In this case, u plus is 0. So along the, you see, this is your curve, that's the curve of discontinuity, okay, the shock curve. So in this part, okay, u minus is going to be 1 and u plus is going to be 0. Okay, so this will give you half. Clear? Therefore, the shock wave is given by is given by x equals to sigma t, right? X equals to sigma t. Okay, so it is x equals to, sorry, not x equals to sigma t, x equals to xi t, xi t. Sigma is xi prime of t. Okay, sigma is xi prime of t. I'm sorry about it. So it's given by, let me just write it down. Okay, it is given by x equals to 1 plus t by 2. Okay, so we have a new shock curve here. You have a new shock curve. This is not a shock curve. This is just a, I mean, sorry, I drew it. I explained it wrong. This is not a shock curve. This is the characteristic curve. This characteristic curve, when it first meets this characteristic curve x equals to r, okay, these are the points where I mean we have a issue, right? Because the characteristic intersect and u is taking multi-valued function. We have to rectify that issue, and to do that we are going to use Rankine-Huguenot condition, and we are getting a new curve here using Rankine-Huguenot condition, which is given by x equals to 1 plus t by 2. Clear? Okay, so what is our weak solution? How does our weak solution looks like? So let me draw that weak solution first one. So maybe let me draw the weak solution first. Okay, again drawing. So this is one. Okay, and how do I put it? X equals to t by 2 plus 1, right? So the slope is something like this. X equals to t. Let us draw the x equals to t line. I think this is x equals to t. I mean, don't. Okay, x equals to t, and so basically this is your x. This is your t. Okay, this is your x. This is your t, and so u. What is the value of u? Okay, let's just draw some curves here. Okay, okay, so this went on the other way. Let me draw another one. Okay, so it's not there is some problem with the software, right? It's going on the other way, but you do realize what is happening. So you know this part is, there are so u is x by t here. Clear? This is exactly the same thing which we did in the earlier, I mean, if you remember the rarefaction thing, there also we did the exact same thing. Okay, right, u is equals to 0 here. Okay, and